I'm happy to introduce our student Mesut Osdemir. I hope I didn't butcher his name because Mesut, you got to know Mesut. Mesut is one of very few people on campus who can say my name perfectly, right, Mesut? So, but Mesut came to us. I'm, by the way, Anish Jantrani. I'm with Biological Agriculture Engineering Department on campus, but I'm mainly part of AgriLife Extension and Research, and I manage on-site wastewater treatment center on Raleigh campus. So Masood came to us a few years back. Time is kind of warped right now, but he showed interest in working with wastewater and use of wastewater to irrigate crops. And that's what I've been doing for quite some time. I said, sure, would love to chat with you, play with you. And he's from Turkey. And the idea there is his government like him to study how to use reclaimed wastewater for irrigation. So with that, I think Masood is working hard trying to collect some data. He's been having, all this COVID and the freezing and everything, kind of putting him back a little bit. But looks like he's on the right track. So Masood, floor is yours. Take it over.
Okay, thank you so much, Dr. Wolfi, Dr. Jantanya, introducing me. So, give me a second. Everybody see my screen?
Looks good.
Okay, so today I'm going to talk about the study that I'm at the beginning of the experimental part, which is not completed yet. My study is to find the effects of irrigation with raw wastewater and membrane bioreactor treated wastewater on soil properties, plant response, and on accumulation of heavy metals in soil and crops. So let's start with the water. We all of us know how important water is. In addition to being one of the essential elements of life, 3/4 of the world is covered with water. It's an essential matter for living organism. Also, we can say it is primary source for economic development and the environment. So there is a total of around 1.4 billion cubic kilometers of water in the world, both groundwater and surface water. 97 of these are in oceans and seas as salt water. The remaining 2.5 percentage is fresh water. Approximately 69% of fresh water is glaciers, while 30% is underground. The rest, 1.2, is on the surface. 21% of these surface water are freshwater lakes. 3.8% is moisture in the soil. 3% in the atmosphere, and the rest of them exist in streams, wetlands, and within the body of plants and animals. So here is the freshwater consumption. As we can see, when we look at the total freshwater withdrawal, so we see that only Asia is more than the United States. This is actually directly proportional to the development of the industrial area. The number of people living in Europe is more than twice the population of the United States. Despite this, the water use on this area, I mean the industrial area, is twice as high in the United States. So wastewater has become an increasingly cost-effective and reliable alternative in countries with arid and semi-arid climates. Wastewater usage without treatment is of concern. Most of development countries suggest that wastewater must be treated before it is released to the environment and used in agriculture. The rate of water used in agriculture is 4/5 of the total. So Here is the advantages and disadvantages of wastewater applications. So the advantages of wastewater applications, fertilization costs can be saved because there are usually plenty of nutrition in the wastewater. Water scarcity can be prevented. Unfortunately, water scarcity is experienced in many countries, so it can be a source for arid and semi-arid regions. If it's used for agricultural purposes, the tertiary treatment system will not be needed, and so additional cost will be eliminated. So here is the disadvantages of wastewater applications. If the nutrients in it are excessive, it may harm the plant and environment. Also, heavy metals can cause a danger to the health of living creatures. Irrigation system can be damaged because of solids in wastewater. So, when we look at the effects of wastewater on soil, there are some uh, studies. It has been observed that soil heavy metal accumulation and salinity problems may occur as a result of the long-term use. It can cause an increase in the amount of sodium with variable calcium, magnesium, and potassium ratios in the soil and may cause salinity and sodicity problems. It may cause toxic effects if plants are watered with wastewater containing high levels of heavy metals. It can pose a threat soil that can be used for irrigation. So here is some research on in the tomato cultivation. So one of is Najafi Iran. Najafi found that the microbiological quality of tomato plant is the best underground drip irrigation with 15 centimeter deep wastewater and also subsurface drip irrigation for waste irrigation minimize the pollution on the soil surface. The other study is Allaham in Jordan. So the heavy metal content in tomato fruit is below these standards. So Allaham studies shows it is possible to use wastewater in tomato cultivation. Another study shows Varie and Tripathi in India. So this study shows there is a health risk because of the excess of heavy metals in vegetable and accumulation in plants. So this and similar studies show each wastewater is unique and poses a risk according to heavy metals concentration level. Because the heavy metal levels in some regions are not high, it does not pose any risk, while it carries a high risk in some regions. So here are my hypotheses and objectives. So I have some research question for my hypothesis. So first, do the heavy metal concentration levels in the wastewater appear to be within the recommended limits? Do the nutrients in wastewater sources improve or degrade soil quality and plant yield? Do heavy metals present in wastewater improve or degrade organic matter? Do the heavy metals in the wastewater mostly accumulate in the soil or plant and fruit? So my objectives are measure the effects of different water types on soil, measuring heavy metal concentration levels in each water type, comparing tomato plant yield grown under irrigation with different water types, measuring heavy metals in the raw and treated wastewater and uptake by soil and plants irrigated with raw and treated wastewater. So the research is carried out in two different regions. So actually, I was conducting my research on Realis campus, but because the portable greenhouse we installed there couldn't prevent damage to plants in the latest extreme weather conditions. So I restarted working in the climate control greenhouse on the main campus. So I obtained the water from Realis campus and grow the plants in greenhouse on the main campus. So here is a picture of the field in Realis campus. Uh, this is the flow diagram of the treatment system. The wastewater comes from a sewer line that serves offices, classrooms, and teaching labs at Texas A&M University. So the membrane bioreactor unit has a 540-gallon trash tank, 540-gallon treatment tank, and a 540-gallon pump tank. The raw wastewater goes directly to the MBR trash tank. So the MBR system allows the hydraulic and sludge holding times to differ from each other. All sludge is aimed at keeping the suspended solids held in the MBR. The size of membrane core is usually less than 0.1 micrometer. So clean and significantly disinfected water is treated on MBR unit. The MBR effluent is treated with ozone before discharge to the Texas Texas A&M sewer line. So it can be transferred to the reverse osmosis unit, which can be removed nitrates and other solids. So the water is returned back to the Texas A&M sewer line, where it goes to wastewater treatment plant for further treatment in the lagoons before being discharged in the Brazos River. So the here is the Texas A&M University main campus Southern Crop Improvement Greenhouse. So plants were placed randomly in 2 blocks and 9 rows. The greenhouse is climate controlled and the temperature is between 20 to 30 centigrade degree, which is good for tomatoes. So irrigation is provided from 3 different water sources. Tap water is used for control water, raw wastewater, and membrane bioreactor treated wastewater are the other water sources. So by mixing these 2 waters in different proportions, 3 different waters were created and plants were irrigated with 6 different water in total. When we look at the soil analysis results that before planting, we see that the soil is loam, while the soil appears to be alkaline with 7.5 pH. Tomato can be cultivated, that type of soil. The soil has calcium and the plants can grow rapidly because calcium helps them to grow fast. So also the salinity in the soil is not too much high. So 7 gallons pots were used to grow the plant, but by putting 20 kilogram of soil, 3/4 of the pot was filled with soil. The large flower pot is important for root development. In this way, the growth of the plant becomes easier. Also, the plant sorceries to keep the possible drained water in the saucer and then enable the soil to use this water. The plant cage will also be used to prevent the plant from spreading around and to ensure the plant's length by swaying. The variety of tomatoes used in the study is Butterboy. A space of 60 to 90 centimeter is required and the plant needs full sun. Harvest is expected within 70 to 75 days after planting. Wastewater is taken from the raw, I mean the left one is the raw wastewater is taken from the tank with the help of the ISCO instrument. For the MVR treated wastewater, the water taken from the MVR unit is provided by a system made by Ryan, the manager of the site. So water quality is measuring with a HANA multimeter. It has the ability to measure many properties: potential of hydrogen, oxidation reduction potential, electrical conductivity, total dissolved solid salinity, dissolved oxygen, pressure, temperature, but I don't need all of them. What I need here is pH and pH, EC, and total dissolved solids. I use for soil moisture measurement, I use an irrometer to measure soil moisture. According to the instruction of this device, the range of 0 to 10 indicates that it is quite wet, while it has sufficient water between 10 to 20 and requires irrigation between 20 to 60. In cases where it shows between 100 to 200, the possibility of the plant being stressed is quite high. The CB is, I forgot to write, CB is centibars. We use the ICP-MS instrument to detect heavy metals in water. Since I don't have permission to use the instrument, I just make the samples ready for the instrument. Because of the total suspended solids of the applied water samples, I need to dilute the raw sample 10 times. Here we see the quality of the water that I have applied. So we can see the average control. Average control has the lowest EC value with the 840 microsiemens per centimeter, while the MVR treated water has the highest EC value with around 1700. So we can all clearly see the turbidity waters. They were ordered from the clearest water to dirty water. So the second clearest water is MVR treated wastewater, while the dirtiest one is the raw wastewater. When we look at the figure of the 519 wavelengths, we can easily see this. Next one. Next one is salinity. So when we look at the table, we can see the ideal salinity values for vegetables. Of course, what matters to me here is what is the ideal value for tomatoes. According to the water I applied, so when we look at the EC values, we see that the control and the raw wastewater are below the reduction value for tomato. It's the below than the one 1500. So however, we see that the other values higher than 1500 but lower than 1900. So theoretically, the yield of product taken from these four water types can be around 5% less than the other two, but this is only when we consider it in terms of salinity. It is possible that we may encounter a different situation when we think that heavy metal is present. So we see the average values of heavy metals in the applied waters. Here we see that any element element other than copper is not above the permissible limit. On the other hand, we see raw wastewater and the mixture of 75% raw wastewater and 25% MBR treated water are above the limit. Hypothetically, if we assume that these waters will continue at this rate, the wastewater should not be used, and the 75% wastewater should be reduced like to 600% in order to remain within the limits. So when we look at the values of two heavy metals, iron and lead, we see that the MBR system reduced the iron and lead values from the T2 is MBR, the T1 is raw wastewater, and here we see the soil moisture values that I recorded with the aerometer. Let's make it more understandable. Then this one is a little complicated. So the values we see in the blue are I recorded just before irrigation. The values we see with the orange are the values 1 day after irrigation. Here I saw an interesting result from 6 irrigation, at least interesting for me. So these values calculated by subtracting the values recorded after the previous irrigation from the values recorded just before irrigation. In this way, soil moisture change was observed between irrigations. So we are looking at T2 and T1. T1 is raw wastewater, T2 is MBR treated wastewater. The amount of moisture in the soil in these two waters is close to each other, and soil moisture is less wet than others. Other waters are not close to these two. I can't say that I know the reason for this yet because my comment when we look at the previous slides again, give me a second. Yeah. The heavy metals in raw wastewater have higher values than the other two water sources, tap water and MBR treated wastewater. And the amount of salt in treated wastewater higher than the MBR treated wastewater is the has the highest EC values. So return back the page. Okay, so this could mean when MBR treated wastewater and raw wastewater are mixed, heavy metals and salts may react to generate hydrogen. This creates the possibility that water can form in the soil as a result of the reaction with the oxygen in the soil. This may cause the amount of moisture in the soil to remain high. Since I have no clear idea and enough data on this issue yet, I only think like this for now. So here is my near future work. I will continue irrigating from now until mid-June. After completing my analysis between mid-June and mid-July, I will evaluate the results until mid-August. I would like to thank especially my chair and advisor, Dr. Gentreya, my committee members, Dr. Gentry and Dr. Wolfe for their contribution to me. I would also like to thank Ryan and Gabriele and other people we work with. And of course, the biggest thank is for the Turkish government. They support me in an opportunity to study in a different country. I would like to do better with more data if I could have, but thank you for listening.
Very nice seminar on a rather dirty subject. Questions?
Hi, Mesut. Do you hear me?
Yes, I can hear you.
Okay, this is Mustafa, by the way. One of your recent slides, you mentioned the salinity of treated wastewater is bigger than others. What is the reason for that? Also, how does treatment system increase the salinity?
Okay, so let me turn back the
Back?
slide. Yeah, that one is
Yes.
right.
Yes,
So
please.
I think chlorine is used for reaction in the MBR unit. This may cause it to react with some metals in the wastewater. For example, wastewater contains magnesium. It may react to form magnesium chloride when disinfected with chloride. In this case, while this magnesium amount decreases, the salt amount increases because magnesium chloride is a salt. This is also possible for sodium. I think it is related to the result of the chemical reaction.
Okay, thank you.
Hello, Mesut.
Hi.
This is Yoji, and I have a quick question. So, did your soil moisture sensor react immediately after irrigating?
I record the reading of the sensor before irrigation and after irrigation. I didn't see it react immediately, so I can't say anything, but I think it's related to drawing water. I read, and also I read there's a buffer is made over the sensor with gypsum, so which helps to prevent the effects caused by accumulation of salinity. Yeah, that's all.
So, does the continuous irrigation would affect the accuracy of the sensor?
Yeah, I think so. So I said there is a buffer made over the sensors with gypsum, so which helps prevent the effects caused by the accumulation of salinity. I think, yeah, the accurate, yeah.
Okay, thank you.
More questions? Is the membrane purification system, is that expensive and or does it require maintenance?
So I think so that the raw wastewater comes from directly to MBR, one of the MBR tanks. So there are other treatment system. The less costable one is the MBR. Before the other steps, it can be more expensive. But I think Dr. Jantranya can answer that question because he's expert on that.
Mesut, you might want to show the audience next time the video how with the pain you took to clean the membrane, right? Remember we had to change the membrane. So the short answer is yeah, the maintenance is there. It's very hard. It takes 2-3 people, including Mesut type, who can lift the membrane out. But in terms of, it's one of the premier wastewater treatment systems. It is expensive, and that's the reason why Mesut is trying different concentration of MBR. So if we can live with 50% MBR, 50% raw wastewater, it would have direct benefit in some cost of overall treatment of wastewater.
I see.